right. I think I'm going here. Uh-oh. Seems to be something wrong. Ah, okay. All right, so we have done several impact problems. We're going to now move to a set of problems that are kind of interesting. We know that if we had two objects, two trains, whatever, hitting each other, where we have A and B, we know we have MA initial, VA initial, plus MB initial, VB initial equals 2. MA final, VA final, plus MB final, VB final. Now this is if the two objects, there are no external forces during the initial time to the final time. Now, this still holds no matter what. And then we have another equation, which is the final velocity difference. It doesn't matter which one you list first, VB final minus VA final, VA initial minus VB initial. Now you'll notice the exchange of the subscripts. If you just remember that all the time, you're all good. So you have these two sets of equations, and these are your friends in solving these problems. But let's look at another problem that is multidimensional. So this works for 1D, but it also works for 2D. It turns out that a two-dimensional or a three-dimensional problem can be broken down to this one-dimensional problem. And let me show you how this happens. Let's say you have a pool ball. It's coming along, has a velocity, and I'm going to make it easy for myself. The velocity, we'll call this A. A has a vector equation, and it's, say, 4I plus 3J. So it's moving along at a speed of 5 units in that direction. Suddenly, it just instantaneously before impact, it hits B. But it hits B along this strange plane here. So here you have a plane. You could call this impact plane here. And then this is the direction of impact. So I'm gonna erase that. So it turns out that I went ahead and aligned this problem such that it aligns with X and Y. As it turns out, no matter how this occurs, you can tilt your head any way you want to align the X and Y to be this way. And I'll show you a problem here in a minute that relates to that. But let's work this one first. Let's say the velocity of B is just equal to 0. So this is the cue ball, and this is maybe the 8 ball or something. Now, how do we determine this? How do we determine, okay, this is just prior to impact. And then the final state is what? Well, first of all, you know, we've got to, somebody has to tell us the coefficient of restitution for us to be able to work this problem. It just doesn't, there's no way around that. So, you know, you can go and test different materials, you can do things, but for the sake of this course, we're going to basically say we're going to be given that. So I'm going to basically say for the moment, the coefficient of restitution is just 1. So it doesn't lose any energy in the impact. And we talked about that last time. So if somebody ever tells you the impact has no energy loss, then that immediately should draw you to that conclusion. But let's go ahead and work this problem. It turns out that this can be broken into two sets of problems. One that occurs along the x-axis and the other that occurs along the y-axis. As it turns out, there's all the impact is occurring along the x-axis. So to work this problem, you would basically use this set of equations on the x-axis. Now what do you do on the y-axis? And that's a point of a little bit of a contention here, and I'm going to describe to you what happens in this text, but I'm also going to describe that actually sometimes that's not exactly what happens in the real world. Let me give you the real world scenario for a moment. Okay, so here's the real world. A ball comes along and it hits a very soft surface. So technically, if it's a pool ball, you could look at this in slow motion with a camera if you wanted to. If it hit at an angle and its E is equal to 1, you get one interesting response, and that it comes off in the same angle. And we'll work a problem like this. If in fact, we'll say this is a solid wall. If in fact E is not equal to 1, or say 0.5 for example, it comes off at a different angle. It turns out that the velocity kind of goes as such. It'll basically tilt down, and we'll work some problems to see this. It turns out while it's in the impact, it's possible that there's some friction between this and that, essentially slowing the component in this direction. Now again, this is where the impact occurs here. This is no impact. However, friction may have actually taken the, okay, so if this is the actual component of the velocity, then this is the component this way. Now, this book says the component in the non-impact direction remains the same. And that's how the problems are worked in this book. Now, if in fact this did occur, you would probably find ever so slight reductions. Say this is 5, and this is 4, and say this is 3. So coming off of the wall, because it has a coefficient of restitution less than 1, say, we'll just say E is less than 1, the value of the ball, the velocity of the ball coming off the wall is going to be less than 3. But this book will say this is maintained, and that's pretty legal for the most part. So the value of the velocity previous to impact, not along the impact, and the value leaving the impact will be the same. Now, if you have a coefficient of restitution less than 1, you hit the wall with 3, you're going to come off the wall with a little bit less than 3. Okay, so the contention that, let me try to focus on the contention here. The contention that this is for before and after is okay with a question mark. However, in the real world, there may be cases where friction because of the impact might reduce this to 3.9 or something like that. It may also have enough friction to have a ball, I'm talking about pool balls, where there's no spin, and when it came off the wall, there's a spin. So it can impart energy, take energy away from this motion, and put it into spin motion here. Now, that's not dealt with here either. So, with this all in mind, let's go work this problem that we've so strangely built. I guess I could have erased this some other way. Okay. So, what do? Here's what we do. We go along and we look at this in the, first of all, let's say, just for a simplification, mass A, mass B are going to be the same, and we'll just make them a unit. It doesn't matter what they are, because if they are the same, they can be divided out of this equation. If they are the same, if masses are the same, and only if and only if the masses are the same, you can rewrite this equation. VA initial plus VB initial is equal to VA final minus VB final. So let's go ahead and start looking at this. Okay, this is along the impact. So let me emphasize that by putting this down. Or better yet, let's put it this way. Along the impact. Now, along the impact, this occurs. So what we have is we have 4 plus, this is 0, is equal to VA final along the x direction plus VB final along that same x direction. I don't have enough information here. Now, luckily, somebody gave us the coefficient of restitution here, and I'm going to write it down first. I'm just going to use the 1 is equal to VB. Well, first let me copy it, and then I'll erase portions. I'll use the eraser here. VF, it's in the x direction, plus VAF in the x direction, VA initial in the x direction, plus minus VB initial in the x direction. Now I can go through here and say, okay, that is a 4, that is a 0, and for our case, this will be a 1. So this equation yields out VB, here, go back to VB final in the x minus VA final in the x is equal to, take that, move it over. I'll just leave the E there for a moment because I might want to change that E some. Now, I'll take this equation over, and it turns out that's a 4. And so I have here. So this equation is going to sit above it. VB final x plus VA final x equals to 4. Add those, and you get something interesting. These cancel each other out, so you get 2 VB final x equals to 4 plus 4e. It turns out, if in fact e was equal to 1, well, let me do one more step, and then I'll say VB final x is equal to 4 plus 4e over 2. If, and we'll start looking at this, hang on. I'll make a little table. E, let's see, how did I do this? Okay. VB final in the X, VA final in the X. And since I've got 1 up here first, I'll do it. VB final in the X, you have a 1 right here. That gives you 4 plus 4. Gives you, knocking out one of those, you'll get a 4. What does VA final equal to? Well, I got to go back to one of these equations. I'm going to go back to the first one. I'm going to say VA final X is equal to 4 minus VB final X. So I'm going to use this equation. If I've got 4 and I put in a 4, I have no motion there. Now, let's look at this. What does this say? It says the final velocity of A. Okay, so we're just looking at A. It goes straight up 3, okay, VA final is equal to 3J. Why? Because, again, the J component is there's no energy taken away there. There's no impact here. So it's just copied to the final state. Then what happens is VB, like right after impact, it goes straight to the right by 4. Oops, VB final equals that. So what it did is it took all of the X component velocity off and transferred it to B. Now, the fact that these have the same mass makes that possible. If the mass were different, that would change a little bit. But don't think that that's a standard. For example, if B were very small, think about it from this case. This is a small mass. So pretty soon it may be so small that it doesn't change the velocity of A almost at all. So the fact that they are exactly the same, when I mean small, I'm talking about the mass. So you could even shrink it down to where this is like an atom and this is a boulder, and essentially there's no appreciable change in the velocity of A impacting this little atom. So let's see what happens with E of, say, 0.5. So you put in 0.5 here, and you get 4 plus, well, 0.5 of 4 is 2, and then that gives you 6 over 2, or it gives you 3. If that gives you 3 up here, then you get a 1 right here. Now, let's go ahead and go to a 0. Okay, if I go to a 0, I get a 2, and that'll give me a 2. And if I get a 2 up here, 4 minus 2 gives me back a 2. So again, what happens is E equals 0, same final velocity. E equal to 1, no loss of energy. So let's verify that energy. So let's do this. Let's go ahead and look at the entire energy state. And now we're going to basically have to identify the mass. What is the energy state of both masses? Okay, first, this has no velocity whatsoever. Second, if you look at this, you'll realize the magnitude of VA, it's a 3, 4, 5 triangle. So the magnitude of VA is 5. So the total energy state is 1/2 m, which is we've identified as that, times 5 squared, or here, 1/2 mv squared, or 12.5. So that's your That is your initial energy. So let me just write that over here. There's no table for it. I guess I could write it down. Energy initial. Okay, it's the same everywhere. This is before impact. Let's now look at the energy final. To do this, I need to recognize the energy final is 1/2, and I'm going to move this up, I think, because I'm going to start playing with the energy final is equal to 1/2 MA VA final squared, and that is the magnitude, plus 1/2 MB VB final squared. So let's look at the first case. Okay, the first case where you have this. Now you have to remember V, okay, this is VB final X, VA final X, VB final Y equal to 0, VB, I meant to say A final Y is equal to the same value as VB final, VB initial A. So that's the 3. So we have to keep this in mind. And now, what we have to do, let's look at it like this. 1/2, the mass is just 1. What is VA final? It is, okay, I'm going to write it down, then I'm going to put the numbers. VA final X squared plus VA final Y squared. And why is that? Because you take the square root of these two, you get back VA final. So in fact, that's the case. 1/2. Yeah, I'll go ahead and put MB. I'll go back and put MA because I'm using symbols right now. VB final X squared plus VB final Y squared. Well, in every single case, we can work. Now, this is not along impact. I can put these values in. They remain fixed. So I can now go in and put 3 here, or 3 squared. And then I can put 0 squared. Okay? These remain the same. Okay, now I'm going to go ahead and take out because now I'm looking at numbers. Let's take case number 1, where it's E is equal to 1. I'm putting in VB final X of 4. Putting in VA final of X is 0. Well, what do I get? I get a 9/2 plus a 16/2. 9 and 16 go back together to give you 25/2 gives you 12.5. Now let's look at this second row. Okay, this second row, I am looking at not a 0. VA final X is that. So I get a 1 squared, and then this one goes up here. Oops. What did I have it? Oh, that must have been the squared term. 3 squared. So now, get 3 squared, 9 plus 1 is 10/2, plus 3 squared is 9, and I get 9/2. Uh-oh, I get 19/2. Ooh, let's see, if I was 20, I'd have 10. So I think I'm 9.5. Because 2 times 9 is 18, and 2 times 1/2 gives you 1. So I'm at 9.5. So now my energy has dropped. Now, let's go back and look at this last one. EA This has to be 2 squared. And this one is 2 here as well. So what do you get? You get 4 plus 9 over 2 plus, oh, there should have been a plus there, plus 4 over 2. 9 is 13 over 2 plus 4 over 2. And that is going to be 6.5 plus 2, or 8.5, I think. So you can see as these impacts take place, lower and lower energy states arise out of a non-perfect impact. And the worst case scenario, of course, is this one, because the two exiting velocities are the same. Now, this is a little bit different than the train. They're not stuck together. Here's why. Here you had this ball coming in like so. And then you had this one sitting dead still. After the impact, what happens is this ball is going up and to the right too. So it's 3 and 2. This ball is going at 2. So what happens is, if you did a snapshot, what you'd see is impact. Then an instant later, you would see this ball would move to here, and this ball would be here. Because this one is moving north, this ball has a component going north. This one only has a component going towards, or I'll say it, in the y direction. This one has a component going in the x. So a few seconds later, this ball could be way up here, but it turns out, if you drew a vertical line, it would touch both of these. It's just what happens is this one's traveling away from this one's traveling that way. They are both going, they both have a component of 2, but they are not stuck together. The y component drags this y component of 3, drags this ball up that contact plane. So actually, if you looked at it, they would impact. A few seconds later, this ball would move directly to the right. This ball would move up and to the right. A few seconds later, this ball would be higher to the right, but this one would be here. A few seconds later, when I say seconds, I'm not sure, it would be here. This one would be way up here. So in fact, this one's going along here, and this one's going along that direction. Now, what time is it? I have no idea. 9:28. So, I'm hesitant to go to the next step because I think that needs to be done from one end of the classroom to the other. But I'll lay it out for what needs to be done. Let's go to another page. And I think I have I have one more page that's empty here. Now let's say you have a ball coming along, but its impact plane, so maybe this ball is going straight north, but the impact plane is like so. I probably should draw it like differently. So here's impact, and here's no impact, or what they might call the impact plane. And so what you have to do, okay, so I'm going to talk philosophically here for the next few minutes, but then I'm going to make this an actual problem next time. Let's say these balls were coming both in this direction. Philosophically, what you would do is you would break it into a component that goes along these directions. And that's very annoying. So you'd make a component going along this direction, and then you would do that over here with this one as well. Then what you would do was tilt your head, so to speak, and make this say the X and this the Y. What you would do is, and now I'm going to color code it again. Oh, that's the same color as the other one. Here, I'll use the green. The green is associated with the X. And since that's already blue, where's that blue thing? This is the Y. So essentially, you would have a set of X equations. So of course, this is before impact. So after impact, the blue just simply gets maintained. So in other words, you would have the velocity of A that would be before impact would be some VAX impact, I being associated with that, plus VAY initial, Y being associated with this one. Now, VA final, that being after impact, would be some particular value here plus the same value here. VAY, and I will say IF times J. So this value, and now I'm going to put that subscript there, initial and final, those are the same because that is along the plane of impact. So that didn't change. Now this you have to calculate using the momentum and the coefficient of restitution, and we'll do that next time. And I'll try to, as a matter of fact, I can remember this problem and I'll just come up with an angle here and work it in class next time. Same thing happens over here. Okay, so if you look at VB initial, VB X initial, I plus VB Y initial before impact, J, VB final after impact is some value. Then I'm going to put a box around. I'm not even going to put this up. This is a special one, but V, B, Y before impact and after impact, the same. That is assuming there's no strange friction that occurs that slows these down. But in the real world, that could happen. So how do you determine these two? Well, now you're looking along the impact. MA, V, A, X, along the X, initial, plus V, oh, I forgot the M. M, B, VB, along the X, initial. Now, here's what I can do. I can say equal. Let's just try to be, here. I'll do a copy. Oops. Oh, that didn't work. Never mind that. I got a seed in there. Okay, I'm just going to write MA, VAX final plus MB, VBX final. And then what I've got is I've got my coefficient of restitution, the final velocity. I can do A first, over Bx initial minus Vax initial. So you solve these two equations to determine what goes in right here. So we will come back and work this problem. Again, let me look at my time. And I think maybe I started a few minutes early. I can't remember. But I think I can't really effectively add anything more to this. I think the best thing for me to do now is come into class on Monday and take a problem like this and maybe just generate a problem. It's very simple and very easy to do this and work this problem from beginning to end. So with that in mind, I will draw everything to a close here.